Hello class. Today we're going to be discussing chain rule word problems. What I did for you all is scanned a couple of problems from the textbook in so that I could talk about the solution to these problems that will all require using the chain rule. So these are problems that should look familiar, but now we know that sometimes the derivative will involve using the chain rule. So if you have your textbook, you may want to open it to page 148. If not, you can go ahead and just look up on the smartboard. Okay, and again, this is the last time we're going to be doing new material before the test. So this is the last big idea day, and it's really just combining what we know about word problems that involve differentiation and having those word problems um, involve the chain rule in their solution. So we have the temperature in Alaska that is modeled by this equation, where you plug in the day of the year. Let's say it's January 1, you'd plug in 1 for X, and it will tell you the predicted temperature on that day. And the problem first wants to get at on what day is the temperature increasing the fastest. So when you think of temperature changing, what function should we be considering? Yep, the derivative. So let's consider how to take the derivative of this function. So we're going to differentiate this sine curve. So to differentiate a sine curve, what is the derivative of sine? That's right, it's cosine. So the 37 comes along for the ride, and the derivative of sine is cosine. And the interior remains the same. It's still 2 pi over 365 times x minus 101. Okay, so this is the cosine, ooh, that's ugly, sorry, cos, that's cosine of the same exact input. And do consider where these inputs come from. 2 pi over 365 means the period is going to be 365 days. And this is a cosine curve shifted 101 days to the right. Okay. What is the derivative? Now, I have taken the derivative of the sine function. I have not differentiated the interior of that sine function, which is right here. So I have to differentiate the inside and then multiply by that derivative. Okay, so we multiply by that derivative. So let's do some side work. Okay, so my side work is taking the derivative of 2 pi over 365, and let's put some parentheses around this puppy, x, oops, sorry, x minus, and I'm just going to distribute the 260, the 2 pi times 101 is 202 pi over 365 as well. So my side work is I'm differentiating this interior of the function, and I did a distribution. Now, we know the derivative of this is 2 pi over 365. Okay, because this derivative goes to 0, and then the derivative of this coefficient of x is just the 2 pi over 365. So moving on to this problem, I multiply by the chain rule that says I multiply by the derivative of the interior, which is 2 pi over 365. All right, so that is the derivative, that is my y prime. So I have y prime, and I'm going to move this 2 pi over 365 to the front just to make it a little more concise here. So 37 doubled, or times 2, is 74 over 365 times cosine of bracket 2 pi over 365 times x minus 101, end parenthesis. So that's my derivative. Well, I want to know when it is increasing at its fastest. So let me get rid of my side work. Hopefully you guys all have that up. I want to know when this is going the fastest that it's increasing. So what I'm determining is when is my rate of change at its highest. Okay, so when is y prime a max? So what you have to consider is when is cosine at a max? Oh, jeez. Okay, so let me undo that business. That's just ridiculous. Okay. Undo. Okay, undo. Okay. When is y prime at a max? So when is cosine at a max? Okay, here we go. Cosine is at a max, number 1, where x equals 0. Okay, so cosine is at a max when the input of cosine is 0. So cosine is the largest at, ooh, and let's do good notation, at cosine of 0, because cosine of 0 equals 1. Okay, so this is where cosine is the largest. So when we look over to this function over here, I'm going to want to ask myself, when am I taking the cosine of 0? Well, the cosine of 0 occurs when x equals how much? Okay, so cosine of 2 pi over 365 times the quantity x minus 101. When is this 0? Okay, it ends up being 0. Oh, sorry. Let's go back. I'll add a new page. New page. It ends up being 0 when x equals 101. Because notice, if I plug in 101 here, I'm going to get the cosine of 0 times that, which is 0. So it's changing the fastest at x equals 101. And this is days. So about what day of the year are we at 101 days? Think about that. I think it might be April. Okay, about 4 months in, 3 to 4 months in. Okay, going back to my problem, about how many degrees per day is the temperature increasing when it's increasing at its fastest? So I'm going to go ahead. This is the derivative function. I'm going to copy, and then let me paste that over here. Paste. Okay, so here it all is. Okay. Sorry, it's kind of going crazy. All right, so back to the problem. This is the derivative, and I want to know what is the rate of increase at the point where it's increasing the fastest. So I know it is increasing the fastest right here at 101 days. So the way I find the rate of increase at that point is I actually am going to plug that value right here into y prime. So let's do it and see what my rate of increase is. So y prime equals 74 pi over 365 times the cosine of, what is this going to be? 0. Okay. Now the cosine of 0 is how much? Right, it is 1. So that's 74 pi over 365. And if we do 75 pi over 365, if I bring up my thing, so let's go 74 pi, 74, let's get rid of this jobby, times pi over 365. Okay, so it's about 0.637, and let's consider our units. Let's get my pen back. Okay, so the original function y was modeling temperature. So this is going to be degrees, but I took the derivative. So now, do you recall how when we do velocity, if we start out with position, that's our distance. So let's say it's meters. We take the derivative of that, and it's meters per second. And we take the derivative of that to find acceleration. We get meters per second squared. So every time we take the derivative, we divide by the time. So here, the time is days. So this is 365 degrees per day. So that means on the 101st day of the year, which I believe is around April, your temperature, your average temperature, is going to be increasing by a little bit over a half a degree per day on average. So in a week, think about it, in a week, your average temperature will have gone up 4.2 degrees. That is some quick growth there of temperature in Alaska. So crazy. That's a big change per day, and that's when it's growing its quickest. Okay, so that is problem 61. If you have any questions, write them down, and I will answer them tomorrow. Now, the next problem I wanted to look at is problem 62, which deals in particle motion. I can go big on this. Oops, lost it. All right, here we go. So we have a position of a particle moving along a line is given by this position equation, where S is in meters and T is in seconds. This one's pretty straightforward. Find the particle's velocity and acceleration at t equals 6 seconds. So I'm going to go a little smaller on this problem. Okay, so right here, I am going to write the position equation in terms of a more user-friendly notation, because I know that we are going to need the power rule to differentiate this square root function. So I'm going to rewrite the position function as s equals 1 plus 4t to the 1/2. So how is velocity related to position? The derivative. So the derivative function is the velocity function. And will I need the chain rule? Will I need the power rule? Sure I will. Bring out all your bags of tricks. So what I'm going to do is first apply the power rule, because my outermost function is the square root. So I am differentiating using my power rule. So I bump that 1/2 out to the front, and then my derivative takes the power and takes it down by 1. So that's negative 1/2 times. Now chain rule, we have a chain of derivatives. Ooh, let's see what this does. So I'm going to, oh, cool. Okay, that's an easier way. Okay, so I have to take the derivative of the inside function. The inside function is this linear function, 1 plus 4t. So what's the derivative of 1 plus 4t? It's 4. Good job. So now I have the chain rule that I applied in that I took the derivative of the outside function, which is my 1/2 power function, and then multiplied by the derivative of the inside. Now, no one in here would leave it this messy. So let's consider 4 times 1/2 is 2. That's my numerator. My denominator is going to be this 1 plus 4t because the power of 1 plus 4t is a negative number. So it is also known as the square root of 1 plus 4t, all that is in the denominator, because this is a negative square root. Okay, so that is my velocities function. So if I am evaluating the velocity at time equals 6 seconds, I am finding v of t. I'm sorry, v of 6. So this is 2 over the square root of 1 plus 24. Yay, it's going to be a rational expression because 1 plus 24 is 25. The square root of 25 is 5. So it's 2/5. And do not forget your units because it really tells a person that you are paying attention to exactly what you're finding. So you're finding the velocity. The velocity is given by meters per second because of the data they gave you in the problem. So next, we are taking the derivative of the velocity function, and that will give us which function? Okay, good. It's acceleration. So we know that s prime, the first derivative, is this business. Okay, 2 over the square root of 1 plus 4t. But this is not very user-friendly for differentiating. So now I have to get it back in a more user-friendly form. So it's 2 times 1 plus 4t. Did I write t squared there? That was silly. Okay, let me erase this squared. Not that. Erase, erase. Okay. So now, let's get my black pen back. Okay, so this is 2 times the quantity 1 plus t squared, and it's a negative because this quantity was in the denominator, and it's a square root, so that's why the power is negative 1/2. So if I consider s double prime, that's my acceleration. So my acceleration equation is found by, again, applying the chain rule. So the outer function is this taking the function to the negative 1/2 power. So when I multiply the power times the coefficient, I get negative 1. All right, now I leave the inside the same, one derivative at a time, and I bump this power down by 1. So what's negative 1/2 minus 1? Negative 3/2. Good, everyone who said that. All right, now I'm going to write this in a more user-friendly form again. So my acceleration function is given by negative 1 over the square root of 1 plus 4t. Oh, let's find my pen here. 4t cubed. Okay, let's think about it. When you take something to the 3/2 power, you cube it and then square root it, because the uppermost, the numerator, represents the power in which you're taking your innermost function, and the 2 represents the root that you are taking. So this is the square root. So this is how you represent 3/2 power, and it is in the denominator because this power is negative. Okay, and I need to evaluate that at time equaling 6 seconds. So I'm taking a of 6. So it's negative 1 over the square root of quantity 1 plus 4 times 6, which is 24 cubed. So 24 cubed, I'm sorry, 1 plus 24 is 25. 25 cubed is 125. And it is 1 over the square root of 125. And if you want to find the square root of 125 and write it as a decimal, you could do that. So I could go over to my calculator and do negative 1 divided by the square root of 125. And so we get negative 0.0. Now take a look here. 3 significant digits, 0.0894. So negative 0.0894. Oh, let's get my pen back. Negative 0.0894. Now, if my units for velocity, okay, let me get my pen back again. Okay, if my units for velocity were meters per second, my units for acceleration are what? Good. Whoa. Undo, fix it, okay. Good enough. Okay, so that is my acceleration at times equaling 6 seconds. So these problems are not any different. They're not new in terms of the big ideas that it takes to go from position to velocity to acceleration. What is new is the fact that you need the chain rule in order to figure out the derivatives. Okay? And do remember you can use the derivative function on your calculator to check your work if you are so inclined to do so. Now, your substitute will be passing out a worksheet for you to work on right now. And that worksheet is IB problems for review. Also, you know that you have book review as well. So that is another thing you're going to want to work on. So tonight, let's choose something fun. Let's do this one. So tonight, I want you to work on the IB problem packet that will be passed out to you. Also, if you have some extra time to work, since you guys can kind of plow your way through those, your Chapter 3 review is out of your book. So 2 assignments. One is what's being passed out. The other is the Chapter 3 review, which is on page 172 to 175. And you're going to want to do the following problems: 1 through 11, 31 to 34, 43 to 46. Okay. 53, 61, 71 to 73, and 76. And I will be here tomorrow and tomorrow night to answer questions for you. Okay, so there's your Chapter 3 review. You also have this IB problem packet, problems for differentiation, that you can work on as well. Have a good day.